Hello, my name is Andy Werfel. This is Luke and Brandon, and our final project for EE23 or 3210 was to take a look at image processing via kernel convolution. So basically, what is the goal of kernel convolution and image processing in general? And it's to either suppress or enhance certain features that you see in a certain digital image. So this could be anything from blurring, sharpening, and edge detection, each of which we'll talk about specifically. But first, we probably want to talk a little bit about how digital media is kind of represented. Your first type of image here is grayscale, and this is where you have basically just a black and white image. It's stored as a two-dimensional matrix and containing integer values between 0 and 255, where 0 is black and 255 is completely white. The next type of image that we'll look at is just your standard RGB image, stands for red, blue, green. And basically, this is just your average color image. It's split into 3 different channels: the red channel, the green channel, and blue channel. And this is stored in MATLAB's perspective basically as a 3-dimensional tensor, which each layer of the 2-dimensional matrix, or each channel is a 2-dimensional matrix that is layered upon one another to create the full color image. And similarly, you have the same kind of scale there, where 0 is black for each of the images, or each of the channels, and then 255 is fully red, fully green, or fully blue. And then you have, if you can sometimes see colors represented in their hexadecimal format, the first, those bits represent each specific color themselves. And then you can get any variety of colors by mixing and matching between those 3 color channels. So now we'll talk a little bit, get more into kernel convolution. But first we need to understand what a kernel is. Basically, all it is an n by n matrix. So a square matrix that has an n value, or its width or its height is basically an odd number. So in this case, we have 2 3x3 kernels. And this one right here is the identity kernel because it's only focusing on the center elements in the matrix. And that one over there you can see has values of 1/9 for each of the values. And it's important that either the sum of all of the values is either equal to 1 or 0, so that you don't mess with these overall magnitude of the values in your picture. So now we'll get into a little bit more of the meat of what kernel convolution is. So basically, you take that kernel, you center it around a certain pixel. So in this case, we're centering the kernel around the baby blue 193 pixel, and then we basically lay the kernel over top that. And what we're doing is we're multiplying the kernel times the pixel value for that specific pixel. So you can see here we have the 2 red pixels. We have 1/9 times 126, and then the next one would be 1/9 times 156. And you basically do that for each consecutive pixel, and then sum them up, and then that is your final value over here that actually becomes your new picture. And this kernel here, you can see basically what you're doing is computing an average, because you're basically summing up all the values around that certain pixel and then dividing them by the number of pixels in total. So it's basically just an average. And you can see the 193 value got basically shifted down to 130 because there were lower values than 193, so it pulled the average down overall. So then basically, to compute the whole image, you just cycle through the entire original image and compute the kernel, just like we talked about for each specific one. One thing to note here is that you can see that we originally start with a 5x5 matrix, and then we have a 3x3 kernel. But you can see that our resulting image is 3x3. So you basically lose, and that's dependent on the kernel size itself. So you basically lose 1 pixel for either side of the picture. So it's basically, kind of compressed.
So specifically for the Gaussian blur kernel, we have, a lot of times we have a 3x3 and a 5x5 they would look like this. So where this bases off of is a Gaussian distribution. So if you took these values of, let's say, like 5 by 5 and had their magnitudes as they were higher, they got like a higher graph here like this. This is kind of what it would look like. So for a larger standard deviation, you're gonna have more of a blur. So where this comes from is it's gonna make this wider, and it's gonna take more of these values from the edges around it. So what a blur really does is it kind of smooths out sharp changes. So if you see that the smaller blur from this cat picture here, it does a little bit less than a larger blur. So the larger kernel. So a larger kernel is going to create more of a blur. So how this kind of works is it kind of acts as a low pass filter. So it's going to get rid of all that noise in an image. So you want to just keep the basics. This is really important when you're doing things like edge detection, so you don't have every little edge in there. So what's really important about this is that you want it to be normalized like a normal Gaussian distribution. So that's where these 1/16 and 1/256 come from. If you add those all up, it adds to that, divide by that, so you get a whole normalized distribution. So if you wanted to do a blur in, let's say, a single direction, so this would be more like a two-dimensional Gaussian distribution. So this would be, obviously, here in the diagonal direction, we have a really large sigma, so it's basically like a big flat area. So what this does is it just blurs in that one direction. So if you look at this cat image, you can kind of see how its eyes split in that direction that the blur is. So how you could use this is if you want to blur something in like one direction, is let's say you want to make something look like it's moving in a single direction, so like you're moving the camera. So with like a car here, it's not moving, but if you add a blur, it kind of looks like it could be. It's really obvious to see the direction if you look at the little boxes behind here. See how like the top part doesn't move at all, but the sides do. So another important, this also kind of shows the kernel size. So this is a lower resolution image, but with a smaller kernel. But you can see it has much more of effect than a really high resolution image with a very large kernel. So another type of kernel would be an embossing kernel, I guess you'd say. And what this kind of does is it kind of creates a shadow whenever there's a change in intensity. So as you can see from this image here, when it goes from a light to dark, it kind of creates this light area right next to the edge. And when it goes from dark to light, it creates this dark image. You kind of see that this is more of like a diagonal part of this that creates this. So, and if you switch where the negatives are in there, you're gonna get the exact opposite effect. So if it goes from, let's say it went from dark to light, if it went from dark to light, it would create a white spot, and if it went from light to dark, it'd create a dark spot.
And so similar to that, we have edge detection. There are two types of edge detection, vertical and horizontal. As you can see up in the top right, those are the two different kernel maps that you can use. One is for horizontal and the other is for vertical. What this does is it takes all of the values around it, like in this picture here, and it sums up everything, and then that it determines whether it is by an edge or not, because if everything would be the same, it would sum up as 0. But since they're not the same, it is not summing up to 0. But in order to do this, it is nice, as stated before, to do a blur, so that way when you're like looking at this picture, this was not blurred beforehand, you can see a lot of the spots that weren't really an edge, it was just a slight shift in color. Once these are all summed up though, if you could imagine that some of these are 255 while others are zeros, it's going to create a final number that is a lot greater than the 255 that we can use for colors. So that does need to be scaled down by a factor of slightly over 1,000. Now you can see here, these are two different kernel maps. They're similar except for the negative signs are flipped around. So you can see on one, the white side is more predominant on the left side, and then on the other, the white side is more predominant on the right side. This is similar to what we had seen in the embossing. And then if you were to sum up both of them, then that would give you your actual vertical edge detection. And then if you look at the vertical versus the horizontal, while these two images might seem very similar to what the original picture looked like, if you look closely, you can see that the vertical edge looks very vertical, while the horizontal looks horizontal as well. Comparing the two images, you can actually see a difference between the two. And so then using Pythagorean's theorem to sum up the x direction and the y direction, you can see what the total edge detection would actually look like.
So now we'll just go a little bit and talk about how you actually compute these kernels. The first way we tried was to basically have a bunch of nested for loops. And this is kind of like an intuitive idea, basically like what we've been showing before, where you kind of just shift across the image and then start and go all the way through pixel by pixel. And that was how we started this because it seemed like the easiest implementation. But we quickly found out that this is actually very, very slow. MATLAB is not optimized to be able to do these kind of for loops and that sort of thing. Like MATLAB is very heavily optimized towards linear algebra. So because of that, we had like that simple flower picture that we had on the last slide. That was about 600 by 600 pixels, and that would take about 30 seconds to compute, which is, probably too long if we were just trying to experiment and everything like that. So then we had to take a different approach, and this one was more geared towards linear algebra, but is a little bit more difficult to understand. So basically, the idea with this method is you have your original image on the front, and your goal is to basically line up all of the surrounding stuff, like all of this, all the pixels surrounding one pixel. You want to line them up in the z dimension. So basically here, what you see is that you have the 193, which is the one we're trying to center around, and then the we shift the image behind it over 1. And you can imagine that this 32 would line up right behind the 193. Now we do that for everything around here until we have basically, one n by m by 3-dimensional tensor, which has basically every pixel has all of its neighbors lined up behind it. And then what you do is basically you multiply the kernel value for each one of these layers and basically collapse that entire tensor down by summing them up. And that leaves you with a 2-dimensional image that has basically had the kernel computation done with it. So this is much faster. Actually, so that same 600 by 600 image, that took about 30 milliseconds instead of 30 seconds, so about a 1,000 times increase. And it's relatively simple code-wise as well, which is nice. And that is the end of our presentation. Thank you for listening.